Hi, and welcome to week 13. Few important things happening this week. Content-wise, typical week. Discussion board is due Wednesday, homework is due Sunday. But I wanted to point out that we have only one more module after this. And what I like to do is combine weeks 14 to 16 into one module. As you know, you're working hard all semester long, and I feel sort of towards the end, we lighten things up and give you the opportunity to sort of recap, connect ideas, and focus more on putting it all together since there are so many bits and pieces, and I know it's been challenging. So week 14 through 16, there's new content, but that new content is sort of how do you pick the best model? Let's compare all the models and start to think about, we've been talking a lot about rate of change and consistent common ratios and constant percent change, i.e. exponential functions, and growing or decreasing rates of change with quadratics and rational functions and radical functions. So we have a lot of content out there. So we'll be focusing on putting that together. And then week 16, the final exam window opens for you to be able to complete it. And recall, please, at the testing center. So in the week 14 to 16 module, I will have the review for the final, and we'll give you all the information you need at that time. So good news on that front. This week, and then with the final exam, when that window opens, you can take it before you're taking more than one class and you want to knock it out early. You're welcome to do that before the actual finals week starts, although you still have into finals week 17 to complete that. So this week we'll be focusing on rational functions in our discussion board. And actually, one of the common things that we do is we purchase appliances and we price shop and we compare. And we often want the best product or the biggest bang for our buck. And in doing so, price is one factor, but longevity, the ability of that product to survive and withstand the test of time, is also a component that we need to consider. So the idea of rational functions will help us to better understand that. So this will kind of be an intuitive introduction. And this week, the content that you'll be focusing on will be to take rational functions, understand their properties, work with them mathematically, be able to talk about things like asymptotes and what those things mean and how to find them. That's going to be our objective this week. Finally, I'm going to go ahead and wrap up the discussion board. A radical drip in the pool was the title. And we had this 12,000 gallon pool that was filled up, and we have this function to model how the water level changes. So we have a hole in the pool, the water begins emptying out, or we have, we're trying to let all the water out. And this is not a bad model because it does take into account somewhat the effects of gravity. Not 100% realistic, but the behavior of this function is much like we would expect. So the first question we have is, how long will it take the pool to drain completely? Well, one way to do this is kind of to graph it and take a look at it and see what happens. But first, let's try to model this mathematically. So our question is, when will the amount of water, the output, when will this quantity, W, be equal to 0? But before we actually then figure out how to solve for T, that is how long it will take, we want to first of all think about how we evaluate such a function if I give you an input. So if we get an input, a value of T, and we want to figure out how much water is left at that time, the first thing we do is we plug in our value of T. So we plug that in for T, and at that stage, once we plug it in, the next thing that we do is we take the square root of that quantity. So we will, let's see here, change my and next thing we do is, well, we're asked to take the square root of this value. So the next thing we do is we have to operate on the T by taking its square root. Next thing we want to do is multiply that. And notice how I say multiply by negative 110, because it's easier to think about addition than it is to think about, have to worry about subtraction versus addition. So we can think about this really as adding negative 110 copies of the square root of T. Multiplication is just a way of taking copies of things. So we're taking negative 110 copies of that. We multiply by negative 110. Once we have that, we now have this full component here. So that gets added to 12,000. And finally, once we add 12,000, we get our output value, which is W. So that's what we would get. That's the process we go through when we plug in a value of the input and try to evaluate it for the output. Now, what if we want to solve for the input depending on what the output is? Well, let's think about this. So we input t, we take the square root, we multiply by negative 110, we add 12,000, and we output the value of w. Now, much like putting something together, to take it apart, you often go through exactly the reverse process. So if we're going to start with an input value of w, we start with an input value of w. So we input the value that we want. So notice how every step we're working our way backwards now, and we're doing the opposite action. So if our last step was to output w, the first step in solving for t will be to input w. So we input 0 because that's the amount of water we want to determine when that amount of water is there. The next thing we did previously in the second to last step is we added 12,000. So the next thing we're going to do is subtract 12,000 from our current value from step 1. Okay, so really what we did here is we subtracted 12,000 from both sides, if that's the way you want to think about it. So that gives us a value. Okay, well, the third to last step was to multiply by negative 110. So in order to get closer to just isolating t, I've got to do the opposite action, which is divide by negative 110. So divide my current value from step 2 that I obtained by negative 110. So I have negative 12,000. Divide that by negative 110. So really what I've done here is I've divided both sides by negative 110. And then my fourth to last step was to square root the value of t. So now because I'm working backwards, the opposite of the square root is to square. That's the opposite action. So now really what I'm doing here is I'm squaring both sides. And so I have to square this ratio here. So negative 12,000 divided by negative 110 is 109.1. So I square that value. And then finally, you can see here that I've isolated the value of t. So after I get the square of that value, which is 11,900.8 hours, that equals the value of t. That may seem like an awful long time, but keep in mind that this was a mathematical model. We would have to kind of figure out what this constant here should be and exactly how this works, but we're not too concerned about where the model came from at this point. So why would it take so long, or why would it take a long time to actually drain? Oh, and by the way, this method that I proposed here, where you kind of go through the steps of how would you evaluate the function, and then knowing that to reverse that process would actually be solving for the opposite variable, in this case, the opposite of plugging in for t and finding w is plugging in for w and finding t. This method works very well often when there is only one term involving the input variable. So one term means anything that's separated by a plus sign is a term. So this is my only term right here. Remember, we thought about this as adding the negative 110 copies of the square root of t, and I only have one term that has the t variable in it. With more than one term that contains t, such as quadratic functions where there is an x and an x squared term, this method will definitely fail. As you know, in order to solve for the input value x, when you're given the value of y for a quadratic function, we have to resort to this thing called the quadratic formula. So the next step we want to think about is looking at how this amount of water is changing as a function of time. So what I can see from the graph of what I have here is that, for instance, let's look at the first change from time 0 to, say, time 2000. So I'm going to look at constant changes in time. And in this case, it's just convenient to look at a change of 2,000 hours. I know that's a very, very long time for this to happen, but nonetheless, after 2,000 hours, I see that I get a gigantic drop in the amount of water that was there, right? I had this much water. Now I only have this much water after 2,000 hours. But in the next 2,000 hours, the drop in the amount of water is far less, right? This amount here, it started here at time 2000. By time 4000, we had lost what? About a little bit over, let's see, that's 6,000, 4,000, about 2,000 gallons of water, whereas over the course of the first hour, we lost about 5,000 gallons. So what we can actually look at is that actual change. So between time 0 and time 2000, time 0 and 2000, we lost about 5,000 gallons. Then over the course of the next hour, 2,000 hours, we only lost about 2,037 gallons of water. These should actually all be negatives because this is a reduction in the amount of water in the tank. in the pool. And so as time progresses over each 2,000 hour interval, the amount of water that leaks out of the pool is lesser and lesser. So there is no real consistency with radical functions in terms of we can't actually think about how much this change is very easily. Like we don't really see any consistency. If you took the change in the rate of change, you wouldn't really see a constant change in the rate of change. Those are called quadratic functions. So there is no real simple way to quantify how much change occurs. The point being that the reason this actually does from a physics standpoint make sense is because you have gravity acting on basically a pool of water. So if we think about a pool of water, there's a lot of water in here at first. And you have the force of gravity pushing down on, you can kind of think about these as sheets of water in here. So let's kind of think about these as rectangular sheets of water. Well, because there's a big force on that first sheet of water, that sheet of water has a force on the next sheet of water, and that adds force on the next sheet, and so on. So down here, there's a lot of force taking place down here because of all these layers pushing down. So initially, the water comes out at a really quick rate. But as that layer moves its way out, now the number of layers of water, and the rectangular layers of water, if you kind of think about it that way, there are fewer of them, and therefore the amount of force on this bottom layer is smaller, and there's less desire for that same amount of water to leak out of the pool. So we can see that because the force has reduced, we actually get a reduction in the amount of water we lose over the next fixed interval of time. So this is kind of how the world actually works. Again, this is not a totally realistic model because 12,000 gallons isn't that much, and if you probably, this would happen much more quickly over the course of, say, 24 hours. But model's a model, so we would want to refine our model, and specifically this term is just too small for that to be the case. So hopefully this has been helpful. I look forward to seeing you guys in the next discussion board, and have a great week. We'll see you soon. Take care.